Hello, I'm John Crawford, here today to give you an overview of Intel's Pentium microprocessor. The Pentium processor is the 5th generation of Intel's line of PC-compatible microprocessors. I co-managed the chip design of the Pentium processor starting back in 1989. I will start out with an historical perspective of Intel's microprocessors from the 386 up through the Pentium processor, and back that up with the underlying historical trends in the semiconductor technology from 1970 through the present. Then I will spend a few minutes describing a few key aspects of the design methodology we used. The bulk of this video is devoted to describing the microarchitecture of the Pentium processor and how the different hardware techniques we chose to include contribute to its performance. After working through this large amount of material, I'll briefly describe the data integrity or error checking features we included. The last section will describe the compiler technology co-developed with the Pentium processor and the results delivered on industry standard spec benchmarks that we achieved with a combination of the hardware techniques and compiler optimizations. Let me start with a brief overview of Intel's microprocessor strategy. We've kept three main goals in mind. First of all, to maintain compatibility. That is, each generation must be compatible with the last in order to carry forward a very large software base and the momentum that comes with that in the market. A second key aspect of the strategy is to maintain a very aggressive performance ramp of doubling the performance every 18 months. The third aspect of the strategy is to continuously add new functions to enter new markets. We've done this in two directions. First of all, we've added functions to move upward from the PC market into the workstation, minicomputer, and mainframe marketplaces, also known as the server market. In the other directions, we've added features to move downward into the laptop, notebook, and handheld, or generally known as the mobile marketplace. So given this as the overall strategy, let's delve into this in more detail. First of all, let's look at the performance growth from the 386 up through the Pentium processor. Spanning a period from 1986 up until the 1993 timeframe, I've highlighted three different generations of processors. You can see 4 points of the 386 line where we offer different frequencies of that product. You can again see 4 of the points of the 486 product line and the first point on the Pentium processor line. Now each of these is plotted in terms of the integer spec performance on the y-axis against general system availability date on the x-axis. It's important to note that this is the date when systems were available from our customers, that is, after they've announced the products and started shipping to their customers through their channels. So you can see here a very nice performance growth rate, and I've had a spreadsheet program plot the regression line on a semi-log chart where it computes the compound annual growth rate somewhere close to 1.6 every year, which corresponds to a doubling of performance about every 18 months. That's a very interesting growth rate. I thought I'd try to relate that growth rate to some real-world examples. We get a little blasé in the computer industry about the performance going up and up every year, whereas if the same growth rate occurred in other areas, it would be truly astounding. For example, given the same growth rate of doubling every 18 months over a decade, you come up with a factor of approximately a 200-fold increase. If the same improvement were applied to automobiles, we'd be traveling around in our cars at about 11,000 miles an hour, or potentially getting about 4,000 miles to the gallon. A point that's maybe a little easier to visualize or to comprehend would be a flight from Los Angeles to New York would take 90 seconds rather than the 5 hours or so that it takes currently. A different way of looking at it might be in the agricultural field, where wheat yields would have gone from about 35 bushels per acre up to about 7,000 bushels an acre. So this is really quite a remarkable growth rate. Now, where did this performance come from? I believe that we've really developed the performance along 3 dimensions. And let me go into each of these in a little more detail. Along one dimension, we have silicon technology. And here with the Pentium processor, we've applied 0.8 micron by CMOS technology as our latest and greatest process. A second dimension is in architecture technology in terms of structuring the computers to extract more parallelism by executing more and more instructions in parallel, using techniques such as superscalar execution, branch prediction, and some more straightforward aspects, such as just larger caches on board and wider buses. A third dimension is software technology, and here improved compilers are key to providing improved performance from maximizing the parallelism that's made available to the hardware. Let's take a closer look at the semiconductor technology dimension. It really is a key aspect that's driving the performance forward. And here we have technology scaling as the main driver, and there are really two aspects of this. One is that the die size grows as we improve our manufacturing processes, and we're able to process larger wafers. We can economically produce larger and larger die sizes. The second aspect is that circuit dimensions shrink, so that each generation we have smaller devices and we're able to print thinner wires and more compact transistors. Fortunately, the smaller transistors run faster, and the extra devices also provide the raw material for integrating performance structures such as caches, extra execution pipelines, and in general, more parallel performance structures. The third category is that new capabilities can also be added using the extra devices that the technology makes available to us. I have here a few charts showing our technology growth from 1970 through the present, where I've charted certain key aspects of our semiconductor technology used in our microprocessors from the 4004 in 1971 up through the Pentium processor in 1993. Here, charting the die size, you can see a nice compound annual growth rate of the die size with a nice regression line, which I've plotted only against the lead CPUs. Coming way below the line at much smaller die sizes, you can see what we call our compaction products, such as the 386 compaction and the 486 compaction. These designs have taken a processor such as the 386 produced on one technology and compacted it to the next generation, so we get a much smaller die size to take into volume manufacturing. If you rule these out and plot just the lead CPUs, we get a very nice compound annual growth rate on the die size that's fairly constant over time. This chart shows the shrinking of the transistor dimensions, and here I have a semi-log plot of the square microns per transistor on the y-axis, trending down over time very nicely. The larger die sizes, compounded with the smaller dimensions for each transistor, combine to produce a very nice growth rate in the transistors per microprocessor. And here you can see a very nice compound annual growth rate of the number of transistors per microprocessor. And here again we can see the compaction devices a little below the line for the same reasons discussed earlier. Again, let's come back to reality and try to relate these growth curves to some real-world examples. The transistor count per die is doubling every 24 months and has been doing so since 1970. That gives us about a 3,000-fold increase over that time frame. Coming back to the real-world examples, perhaps the best analogy is the one of the wheat yields. Again, back in 1970, the typical yield was about 33 bushels per acre. If we had a 3,000-fold increase, that would give us about 100,000 bushels per acre. And that would be about 3 feet of wheat piled up on that acre. Perhaps the only real-world example that's come even close to this growth rate is the growth in our national debt. But I haven't had the courage to work out the figures on that one. Let me shift gears now back to the present and bring you to the Pentium processor. First of all, I'd like to cover two key aspects of the design methodology used in developing this processor of the many that were involved. One is that we co-developed software with the hardware so that they would complement each other to deliver maximum performance. In order to do this, we had a big focus on compiler technology. We staffed and funded a very professional compiler team internally so that the compiler developers could work hand in hand with the hardware developers. We also wanted to ensure that this compiler technology was propagated out to our large community of applications developers. So it was very important to make this technology broadly available and not hold it close to our vest. Consequently, we had a big focus on working with external compiler vendors to deliver this technology out through their channels. Later on, we'll hear from the manager of our internal compiler effort, Beatrice Fu, who will describe this compiler technology and the results that we achieved. We also work closely with key operating system vendors to make sure that the system aspects of the processor would result in good delivered performance from these operating systems. A second aspect of the design methodology was quantifying the design decisions, and the focus here was to quantify decisions on the architecture features to include, that is, what new features to add to the instruction set, and to quantify decisions on the microarchitecture, that is, the internal structure of the processor, and the compiler techniques, the internal structure of the compiler, if you will. We wanted to base decisions in these areas on as much quantitative data as possible. One technique we used was system measurement, where we could measure programs executing on 386 and 486 systems and project forward to the Pentium processor from these system measurements. At a more detailed level, we developed a very flexible and detailed performance simulator that would very accurately estimate the performance of different software running on the Pentium processor, long before it was realized in silicon. In order to drive the simulator, we collected a number of traces across a broad spectrum of application areas and used these traces to drive the performance simulator. The results of this trace-driven simulation gave us some quantitative feedback on the value of the different aspects of the hardware and software. We even carried this quantitative computer architecture into the hardware itself by providing a number of facilities within the processor to support measurement of running systems, so that we have a very nice event monitoring facility that can count both discrete events, such as cache misses, as well as some duration events, such as bus stalls. Later on, we'll see how we use these performance monitors to measure the effectiveness of some key microarchitecture techniques included in the Pentium processor and how they performed when executing the SPEC benchmark suite. But first, let's hear from Don Alpert, Chief Architect of the Pentium processor, who will describe key features of its microarchitecture.
Thanks, John. When we started the design of the Pentium processor, we knew there'd be a number of very important challenges in trying to stay on the performance treadmill while maintaining compatibility with the previous generation of Intel microprocessors. What I'll be describing here is a number of the microarchitecture techniques that we developed in designing the Pentium processor. The topics I will cover are the bus interface, superscalar integer pipelines, cache organization, branch prediction, and pipeline floating point unit. Let's start with the bus interface. We needed a high-performance bus to satisfy the Pentium processor's demand for instructions and data from external cache and memory. The data bus is 64 bits wide and operates at the full 66 MHz speed of the processor core. In contrast, the bus of our previous generation processor, the Intel486 Model DX2, has a 32-bit data path and it runs at 33 MHz. So the Pentium processor's bus has 4 times the bandwidth, with a peak rate of over half a gigabyte per second. Now moving on to the integer execution units, we started with a 5-stage pipeline based on that of the Intel486 processor. The first stage reads instructions from the cache into a prefetch buffer and aligns them for decoding. The first decode stage generates a control word for execution by the pipeline. The second decode stage decodes the control word and generates addresses for memory references. Each stage is used either to calculate a result in the ALU or to access data in the cache. The final stage is used to write results back to the register file. In the Pentium processor, we have improved performance by decoding 2 instructions in parallel and replicating the address generation hardware in ALU. You can think of this as being similar to placing 2 of the 46's integer pipelines on the same chip. We call the 2 pipelines U and V. One final point is that complex instructions, such as string operations, are executed by generating a sequence of microcode words in the D1 stage. The microcode is written to take advantage of the hardware that's available in both pipelines. Let's look in more detail at the instruction decode stage. Logic in the D1 stage is used to check for dependencies between instructions, and we only issue instructions in parallel to the 2 pipelines if they are independent. The types of dependency that we check for are resource, control, and data. First of all, we check that both of the instructions are from a class we call, and this is in quotes, simple. The so-called simple instructions include ALU operations, jumps, loads, and stores. Our definition of simple even includes instructions that perform operations from memory to registers. We find that about 90% to 95% of instructions executed are simple. By issuing only a subset of the instructions in parallel, we're able to handle resource dependencies. For example, there's only a single shifter in the U pipe, so all of the shift instructions are issued to the U pipe. Control dependencies occur when the result of one instruction determines whether another instruction will be executed. We handle these by checking whether the first instruction is a jump instruction. If it is, then we don't issue an instruction in parallel. Data dependencies occur when the result of one instruction is used or modified by another instruction. We handle these by checking that the destination register of the first instruction is neither the source nor destination register of the second instruction. We have included logic to improve performance by handling some common cases of dependencies, thereby allowing more instructions to be executed in parallel. First of all are flags. In the Intel architecture, most of the instructions modify the flags, so that without special handling, it would be difficult to pair many instructions. So we do handle the case of parallel instructions that modify the flags. and we update the flags the same as if the instructions were executed sequentially. We also have special logic that handles the case for conditional branch instructions executed in parallel with an instruction that sets the flags. This occurs quite commonly, especially for compare branch combinations. A second special case was the logic on the stack pointer that allows pushes and pops to be executed in parallel. For example, when passing parameters for a procedure call, there will often be a sequence of pushes. The logic adjusts the stack pointer appropriately for parallel execution. One final point about the decoder is that we prefetch a complete cache line of 256 bits to keep the decoder busy. So the question comes up, just how effective is the instruction pairing? Here's a chart showing how the pipelines are utilized on the SPECint 92 or integer spec benchmark suite. What I've plotted here is for each of the spec benchmarks, the percentage of instructions that go in the U pipe, which is the primary pipeline, and then the percentage of instructions that go through the V pipe, which is the secondary pipeline. You can see that the pairing ranges roughly around 30 to 40%, with one benchmark, Equintot, hitting above 40% of the instructions going into the V pipe. You can see on this particular set of applications that the pairing is quite effective. I would like to point out again that these measurements are taken from an actual running system using the performance monitoring counters that John described earlier. At this point, let's take a look at the cache organization. We have separate code and data caches. This was done to eliminate the conflicts between prefetch accesses and data accesses. This was important because we knew the branch predictor was going to drive a lot more references into the code cache, and because the superscalar pipelines would generate two data references in parallel. A consequence of splitting the caches is that we have to add extra logic to handle self-modifying code compatibly. This affected a couple of key areas. One is that each cache has to snoop the other cache's misses, so there would never be inconsistent data in the two caches. It turns out that the logic that handles consistency between external memory and the on-chip caches was able to handle consistency between the on-chip caches as well. The other aspect is that we had to snoop the prefetch buffers also, so that if, for example, we wrote to an area of memory that happened to be in a prefetch buffer, we would need to invalidate the prefetch. Now we can look at some of the vital statistics about the caches. Each of them is 8 kbytes in size. They both use 32-byte lines and are two-way associative. The data cache uses a write-back protocol to minimize the bus traffic, and we use a MESI, that's MESI 4-state protocol, to keep the data cache consistent with the code cache, as well as the rest of the system, including multi-level caches off-chip and the memory. Once we separated the code and data caches, it became effective to separate the TLBs as well. The TLBs support two page sizes, a 4 kilobyte page and a 4 megabyte page. The larger page is useful for mapping large resident data structures with a single TLB entry. For example, it can be used to map a graphics frame buffer or the memory resident portions, either code or data, of the operating system. The data TLB has 64 entries for 4 kbyte pages and 8 entries for 4 megabyte pages. The code TLB has 32 entries for 4 kbyte pages. The effectiveness of the caches is shown on the following charts for the SPEC benchmark suite. Please remember that this data is taken from an actual running system using the performance monitoring hardware that we included on chip. The first chart shows the hit rate for instructions. It varies from about 90% to a little over 95%. What we are showing is the hit rate for prefetches of 32-byte lines coming out of the instruction cache. This is often reported in terms of hits per instruction instead, and if we looked at it in this way, the rate would even have been higher. The next chart shows the data cache hit rate based on the hits per read or write reference to memory. You can see that here, the data cache hit rate varies from just below 90% to about 95%. One of the most interesting aspects of the data cache's design is its support for dual accesses by the two pipelines. The Intel architecture has a limited number of registers. There are only 8, and that results in more data memory references per instruction than we would see in architectures that have more registers. For example, for optimized 32-bit code, we see about 0.6 data references per instruction. In contrast, many of the RISC architectures that have 32 registers would see only about half that number of memory references per instruction. Now, even a small cache can capture the locality of the additional references. We see that the compiler for the RISC processors can capture all those references in the 32-register file, but it does lead to a requirement for additional bandwidth in the Pentium processor. We have implemented the cache using dual-ported tags and TLB. with a single-ported interleaved data array. Making the data array, which is the bulk of storage in the cache, single-ported, turned out to be the most efficient use of area. If we had also made it dual-ported, we would have had a smaller cache and consequently higher miss rate. The effect of increased misses was more than the impact of bank conflicts, so we went with the interleaved approach. There's logic to detect when parallel references go to the same bank. When they do, the U-pipe reference is completed, and the V-pipe is forced to stall for one clock. The same logic also handles the case of data dependencies between parallel references, because of course, if two references are to the same location in memory, they will necessarily be to the same bank. One final point about the data cache is that the two 32-bit paths are combined together to form a 64-bit path for double precision floating point operands. The next chart shows some measurements taken from the SPEC integer benchmark suite, demonstrating the effectiveness of dual memory reference support. The chart shows the frequency of references that are actually paired. You can see here that except for equintot, about 20 to 25% of the memory references are V-pipe references paired with U-pipe references, and the rate of bank conflicts is low. Equintot shows 40% of references executed in parallel in the V-pipe, but about 1 out of 8 references is a conflict. One of the most important performance enhancements of the Pentium processor is dynamic branch prediction. The Intel486 processor flushes its pipeline for every taken branch, at a cost of 2 clocks delay. Taken branches amount to 15% to 20% of instructions executed, representing an opportunity for substantial improvement. In the Pentium processor, we cache information about previous branches and use this to predict future branches. The prediction is made at an early stage of the pipeline, and when the prediction is correct, we can execute branches with no delay. All of the branch predictions are verified at the end of the pipeline. If the prediction was incorrect, the pipelines are flushed at a cost of 3 or 4 clocks. The techniques are similar to those used in mainframe architectures, with adaptation to the Intel architecture and to superscalar execution. The memory structures that are used in the branch prediction hardware make for very efficient VLSI implementation. The heart of the branch prediction hardware is an associative memory called a branch target buffer, or BTB. The BTB has 256 entries, and it is 4-way associative. The tags used to access the BTB is the address of the branch instruction. The data portion of the BTB includes the branch destination address and 2 bits of history used to predict whether or not the branch will be taken. Using 2 bits of history helps in cases where a branch is consistently taken for a while, then occasionally not taken. Only when the prediction is wrong twice in a row will the prediction be changed. We have some measurements of the branch prediction accuracy, taken with the built-in performance monitoring hardware. As you can see, the branch prediction accuracy is generally 80% to 85%, with the exception of the GCC benchmark, which is only 73%. The transistor budget available in the Pentium processor allowed for dramatic improvements in the floating point performance. In the Intel486 microprocessor, the floating point unit wasn't pipelined, and it typically took 10 to 14 clocks for most operations. The faster hardware algorithms in the Pentium processor allow the operations to be executed by a factor of 3 or more faster. The execution units are also pipelined to deliver 1 floating point result per clock. The floating point pipeline was closely integrated with the integer pipeline. This was important in optimizing for memory-to-register operations to deliver 1 64-bit memory reference per clock in parallel with 1 floating point operation. The floating point execution units support the 80-bit IEEE extended format with short latencies. The multiplier and adder have latencies of 3 clocks for all formats. The divider has a latency of 18 to 38 clocks for precisions from single to extended. Along with the hardware to improve performance of the basic arithmetic functions, we also re-implemented the transcendental instructions, sine, cosine, logarithm, and exponential, that are part of our instruction set. The new algorithms use polynomial approximations to take advantage of the fast multiplier and adder. This provides improvements both in performance and accuracy over the Intel486 microprocessor. A key aspect of the floating point performance was co-developing the compiler with the hardware in order to ensure that this pipeline structure would be very effectively used. So that completes my portion of the presentation. I hope that it helped you in your understanding of the Pentium microprocessor.
Some of the new capabilities we included on the Pentium processor were increased error detection and a functional redundancy check mode of operation. These were included at the request of our customers at the high end of the computer market, those involved in delivering solutions to mission-critical server applications. In these areas, even extremely rare errors must be detected and handled appropriately. So we included these features to satisfy those requirements. The most important thing is to handle external errors. And here we've carried forward the data bus parity generation and checking logic that was on the 486 and extended that to our 64-bit data bus. Also, we added a parity bit on the address bus so that we also can cover the second wide bus going off chip with parity generation and checking. In addition to this external error detection capability, within the chip, we've included parity bits on all the major arrays. This includes the code and data cache arrays, cache tag arrays, the TLBs, and even the microcode ROM. All of these have parity bits included so that any internal errors are detected and are reported via a pin. This internal parity checking covers about half the devices on the chip, and so provides a very nice basic level of coverage. Beyond that, in order to offer an option for the ultimate in error detection, we have an FRC, or functional redundancy check mode, on the chip, where you can configure two processors in a master checker configuration, where the master is operating normally, and the checker, rather than driving its output pins, turns them inside out and checks the values driven by the master and pulls a pin only if a mismatch occurs. So this increased error detection level provides a nice capability for certain new application areas where the ultimate in error detection is required. And now let's go with Beatrice Fu to our performance lab, where she will describe the compiler technology we developed with the Pentium processor.
Thanks, John. How compiler technology enhances the performance of the Pentium processor is best illustrated with a simple example. Here we have a simple synthetic program compiled by two compilers. The code on the left-hand side is generated by a typical 486 compiler, and the code on the right-hand side is generated by the new compiler technology optimized for the Pentium CPU. The two code sequences are quite different, even though they are both correct representations of the original program. This demonstration shows how the two code sequences proceed through the Pentium processor. The graphical block diagram represents the instruction cache, the data cache, the two execution pipelines, as well as the floating point unit. While executing, the active instructions are color-coded so that we can follow the journeys through the Pentium processor. As can be seen, the Pentium processor has many idle resources on the left-hand side when executing the traditional code sequence, whereas the new code sequence utilizes the dual execution pipelines more effectively on the right-hand side. As a result, the time taken to run the new code sequence is much less than the traditional code. As can be seen, the right-hand side is finished, whereas the left-hand side is still chugging along. The advancement of CPU microarchitecture requires advanced compiler technology to exploit the on-chip parallelism, such that features like pipeline and superscalar can be made more effective to deliver the final performance as illustrated in the previous demonstration. The role of a compiler has always been translating high-level language into low-level machine code so as to hide the machine details from many programmers. The role of an optimizing compiler is to generate machine code that runs efficiently on the target processor. In the simple example here, a traditional compiler will generate code to increment the array index and compare the loop bound and end up with a 3-cycle loop body. Using the same example, our optimizing compiler displaces the loop count to eliminate the compare instruction and take advantage of the 0 flag setting of the increment instruction, which improves the loop cycle count from 3 down to 2. We are again using the same example. Our new compiler technology further unrolls the loop and overlaps the instructions from two different iterations to take full advantage of the superscalar core. This gives a 2-cycle loop count for every 2 iterations, or effectively 1 cycle per iteration. This is one example of how our compiler technology maximizes the usage of the dual pipelines of the Pentium processor. In the last decade, the CPU speed has increased more than 10 times, but the speed of memory components has not kept up. As caches are introduced into the memory subsystem to meet the CPU demand, cooperation from compilers is sometimes needed to ensure efficient use of the memory bandwidth. In this example, with J being the index of the innermost loop, the array elements are not accessed from contiguous memory locations. In other words, even though several elements are brought into one cache line, only the first element will be used. The rest will be discarded and brought in again and again as we cycle through the outer loop. Our compiler technology remedies this by interchanging I and J, making the memory accesses contiguous. Just now I illustrated a few techniques of our optimizing compiler. Our 32-bit compiler has extensive optimization to ensure the maximum performance of the Pentium processor. We have state-of-the-art classical optimizations like register variable detection, loop invariant co-motion, and others listed here. We also pay specific attention to the x86 architecture as well as our CPU implementation in terms of selecting effective addressing modes and code sequences and rearranging instructions to take advantage of the superscalar core. In the earlier example, I illustrated how loop interchange can result in more effective use of the memory bandwidth. Loop interchange is only one of the memory optimization techniques. Our compiler technology can also perform loop distribution to promote parallelism, blocking to maximize memory reuse once loaded into the cache, strip mining to adjust the problem size to the size of the cache in order to minimize thrashing, and cache preloading to hide the memory latency. The next chart shows the result of our compiler effort. We are comparing the performance of the 66 MHz Pentium processor running the SPEC benchmark suites compiled by 3 different compilers. The compiler technology I just described is shown here. Compiler A is the best available 486 compiler, and compiler B was an average compiler in 1990 when we started the compiler effort. On the integer side, we were able to go from a performance level of 41 using the average compiler up to a level of 64.6 using our new compiler technology. When compared to the level of 57.6 from the best available 486 compiler, the difference between the best 486 compiler and the new compiler is on the order of 10 to 15%. And obviously a very substantial improvement over the average compiler from the 1990 vintage. On the floating point side, the results are even more dramatic. From the new compiler technology, we are able to achieve a SPEC floating point of 59.7 compared to a much lower numbers in the 30s using the other compilers. Throughout the development of the new compiler technology, we emphasized that we could not optimize performance of the Pentium processor at the expense of the Intel486 or even the Intel386 processors. So we were very careful in implementing our optimization techniques, and we constantly measure the performance of the generated code on the older generation processors. The efforts really paid off. This chart shows that instead of optimizing for the Pentium processor at the expense of the older part, we were in fact able to improve the performance on the older part while optimizing for the Pentium processor. We are again comparing the same benchmark suites using the same 3 compilers but running the code on the Intel486 processor. You can see that our new compiler technology is providing a nice performance boost, not only over the average compiler that we had in 1990, but also over the best available 486 compiler. Now I hope you can see the importance of compiler technology to the overall performance.
This concludes our talk on the Pentium microprocessor. I hope that you'll take away from this talk some understanding of the key microarchitecture features inside the processor, as well as some of the key techniques we've developed with compiler technology. In combination, these two producing a new level of performance within our line of PC-compatible microprocessors. Thank you.